Hi everyone, my name is Harper Stewart and I am beginning my second year as a PhD student. I work in Dr. Jill McNick-Gray's Biomechanics Research Lab at the University of Southern California in Los Angeles, and my work is titled Differences in Ground Reaction Force Time Characteristics Experienced by Females when Running on a Track at Different Speeds. So the background of this study is that there's a high incidence rate of stress-related injuries in NCAA Division I sports for up to 30% of athletes. And endurance runners are a population that's particularly susceptible to sustaining these injuries. Running-related stress injuries occur in the pelvis and the femur, but the most common occurrence is in the tibia and metatarsal. And the locations that sustain the most injuries are also closest to the point of force application during running, which is at the foot. So to understand why people are more likely to experience stress-related bone injuries from running, we need to think about how load is distributed across bones. So from a materials perspective, bones are strong when force is applied in the axial direction, but not when it's applied in the transverse direction. And then, as soon as this force is oriented differently along the axis of the bone, muscles must be active in order to control the moments that are applied at the knee and the ankle. And then when the point of force application changes along the foot, the demand on the system also changes as these moments are redistributed. So this is the lens that we're using to try to achieve the overall aim of our larger collaborative study to identify individual runners that are at risk of developing stress-related bone responses. And to prospectively identify these athletes that might be at risk, we're collecting biomechanical data over time. And this force and inertial measurement data will allow us to detect changes in training patterns. But before we're able to characterize what constitutes a significant change due to an oncoming injury, we need to first understand what changes in the individual biomechanical data are a result of changes in speed. So therefore, the specific aim of this work was to characterize the difference in ground reaction force time characteristics at different speeds. So before continuing, I want to point out some different components of the force time curves that are shown on this graph. So we have the vertical component, the anterior posterior component, and the medial lateral component. And this film strip is also showing the force vector overlays of the participant running across the force plate. And the green arrow is the resultant force vector, and the series of 5 photos match up with different points on this force time curve. So for example, touchdown matches up with this point on the force time curve. So our hypothesis regarding foot contact duration was that it would decrease as the running speed increased. And we wanted to compare our data with this previously established trend in the literature, but also look within participant to see if this was true for each runner individually. Next, we predicted that as speed increased, the peak vertical force would increase because as the athlete runs faster, they have a shorter amount of time to apply force. And this measurement functions as an indicator of how load is changing with speed. We also examined braking duration, which is the period before the anterior-posterior force crosses 0, and we expressed this value as a percent of foot contact duration and predicted that this would remain the same as speed increased because steady-state running requires equal amounts of braking and propulsive forces in order to maintain speed. Also related to the braking phase, we predicted that the magnitude of the average braking force would increase with speed. And we chose this measurement to characterize how the load is changing, particularly during the impact portion of landing. So this is an example of one trial from our experimental setup. You can see the participant running across the force plates. So we had 8 female collegiate and post-collegiate NCAA division runners that volunteered to participate, and the participants wore their typical running sneakers during the experimental collection. We collected the following data during the experiment. Force was gathered using 2 Kistler force plates sampling at 1200 Hz. We also placed 3 APDM inertial measurement units on the participants and sampled at 500 Hz. 2 high-speed video cameras were recording all the trials at 240 Hz to capture the frontal and sagittal view during running. And then finally, 2 Broward timing gauges were used to ensure that the athletes were running at the correct pace. Our athletes were asked to run on a level outdoor track at 7 and 5:30 mile paces, which are speeds typical for training, and 10 contacts were collected on each foot for each speed for a total of approximately 40 contacts per participant. So our first hypothesis that foot contact duration would decrease as running speed increased, we found that this was true for the group and also for each individual participant. We also hypothesized peak vertical forces increase, and we found that this was true for the group but only for 6 of the 8 participants. So this figure on the right is showing the peak vertical force for all trials for each participant, and the individuals with a significant difference between speeds are indicated by the yellow box. This green circle is an example of a participant where the peak force increased, However, this red circle shows a participant where the change in peak vertical between speeds was not significant. And this shows the importance of looking at each individual person's data in order to determine their potential for injury, because each person might not be following the group trends. So our hypothesis specifically about the braking phase included that the percent of braking within total contact would remain constant as speed increased. And we found that this was true for all 8 of our participants. So this is showing that the proportion of contact spent in braking did not change as the speed increased. We also predicted that the average braking force magnitude would increase as speed increased, and this was statistically significant for the group and for 7 of our 8 participants. And this is important because while we found that the proportion of contact spent in braking remained the same, increasing the braking force magnitude is showing that the load during the braking phase is increasing. Again, this figure on the right is showing the spread of the individual trials for each subject, and all of the subjects except for participant 1 experienced greater average braking force magnitudes. Again, green circle showing a significant difference between the 2 speeds, while the red circle is not showing them. And then here is an overall summary of our major findings, along with 2 additional quantities that I didn't discuss in this presentation, but please feel free to check out my conference paper for a full overview of our findings, which includes the change in vertical velocity and the change in horizontal velocity during the braking phase. And the dots indicate the group significance, while the small people indicate the number of participants who exhibited the same trends within their individual data as the speed increased. So we also looked at how the orientation of the force vector in the sagittal plane changed. So we created these graphs which are documenting the force vector orientation angle and how that changed relative to vertical during contact. So this video that I just showed ended on a negative sagittal plane ground reaction force orientation, because we can see that the force vector is opposing the athlete's intended direction of motion, which is to the left. This second video shows the force orientation when it's vertical. So that's defined as this 0 crossing on the graph when this force vector is vertical. And then this video is demonstrating a positive sagittal plane ground reaction force orientation, because the force is pointed in the athlete's intended direction of motion, which corresponds to a positive value on this graph. So this is an example of the orientation of the reaction force in the sagittal plane, and we have 2 exemplar trials shown here. And if you look to the left of the black vertical line, you can see that there are similarities in the force orientation regardless of speed. And then overlaying these trials by participant, we noticed that the force was oriented the same way during what we've labeled as this initial phase of contact. And this is really interesting because although the athlete was running at 2 different speeds, the orientation of the reaction force in the sagittal plane during this phase follows a consistent pattern. And we believe that this is important because the consistency shows that the nervous system is prioritizing the orientation of the reaction force when initiating contact. So we chose to look at contact time and percent time in braking to understand how the data from our individual participants corresponded to findings of previous literature. And we chose to look at peak vertical force and average braking force magnitudes in order to understand how the load changed during the contact period with speed. And then throughout the process of studying each participant closely, we also found that the orientation of the reaction force during the early portion of the braking phase was comparable across speeds within participants. So in the future, we want to determine how this force is oriented relative to the lower limb segments to help us understand the demand on the lower extremity. And this will help us build out the foundation to eventually prevent stress-related running injuries. We acknowledge that the sample size of our study is low, but we're working to increase the number of participants as well as gather associated data about injuries, race performance, training loads, and biological factors in order to help prevent future injuries. I would like to acknowledge all the members of the USC Biomechanics Research Lab for supporting and helping out with this work. And I would also like to thank my funding sources, which are the Pac-12 Student Athlete Health and Wellbeing Grant Program and the Los Angeles chapter of the ARCS Foundation and USC WISE. So thanks so much for your attention. Here's my email if you have questions. Bye, Don. And these are my citations. Thank you.